Welcome to Engineers Mindset. Okay, so in today's class, I'm going to be showing us how to derive the basic equation for torsion. Now, let's consider that we have a cylindrical section. Of course, whose end is fixed at one point and free at the other end. So this particular end is actually fixed, and then this end is free. And now let's say we apply a torque. Okay, let's say we apply a turning effect torque. A torque is simply what? A turning force or a turning effect on this end of the shaft. Okay, this can also be called a shaft. So let's say we apply a torque on this end of the shaft, and since here is fixed, if we rotate this point, let's call this point B, and let this be called the origin of this cycle or the circular portion of the shaft. Now, since this end is fixed, if I apply a turning effect on this other portion, since here is fixed, there is going to be a shearing of this surface. So this surface will actually what? Shear or tilt in this direction. Okay, we'll have here to undergo what is called shearing. So this will actually change position from this point down to this position. Okay, because here is fixed and here cannot rotate. Since this end cannot rotate, if we turn about this point, then it has to shear towards here. This position B will change position to this point. So let's call it here B prime. That's to say the change in position from point B down to this position. We'll simply call that B prime. Okay, so like I said, since here is fixed, there is going to be what? A shearing that will occur there. So let's call this the angle of shear, simply psi. Okay, let's call this angle the angle of shear or the shear strain. Okay, so where shear, where psi equals the shear strain, okay, equals the shear strain. All right, due to the torque that is being applied to this surface. All right, so let's call this point A. Okay, and of course, we notice now that we can trace this point, of course, down to the center of the cycle. If we do that, also due to this rotation, there is going to be a twist on this surface. Of course, there's a torque that is being applied there, so that torque will actually cause a twist on this surface. Let's call that twist theta. This twist is called the angle of twist. Okay, so theta is actually called the angle of twist. Okay, due to the applied torque on this surface. So theta is simply called the angle of twist. All right. Now, if we observe now, notice now that A, B, and B prime is actually forming a right angle triangle. A, B, B prime is forming a right angle triangle. Also, O, B, B prime is also forming a right angle triangle. So we'll get back to all of this. Now we're talking about torsion. Torsion is simply a force that is being caused or applied on the shaft. A force that is being applied on the shaft, which causes the shaft to undergo a rotary motion. That's what torsion is all about. Okay, which causes the shaft to undergo a rotary motion. And that force is simply called what? Torque. Simply the product of force and the radius arm of the shaft. All right. Now, majorly, now since we said that this torque causes a rotary point, and then we'll have, since we said the torque causes a rotary motion on this surface, and then this other point shears because here is fixed, then it means that the shear stress is actually equal to the shear strain. Recall in normal stress. Recall in normal stress, we simply say that stress is actually directly proportional to what? Strain of the material. So if we remove proportionality sign, we always introduce a constant. So we simply have that stress is equal to what? The constant, which is now the Young's modulus of the material times the strain of the material. The same thing happens here. Since this portion is undergoing a shear, then it simply means that the shear stress, okay, it simply means that the shear stress, of course, is directly proportional to what? The shear strain. So it means the shear stress is directly proportional to the shear strain because that portion is actually what? Undergoing a shear. So the shear stress is directly proportional to the shear strain. And symbolically, we know tau to be the symbol for shear strain. So it simply means, we know tau to be the symbol for shear stress. So it simply means shear stress is directly proportional to shear strain. And I said this angle psi is the value for what? The shear strain. So simply shear stress is directly proportional to, of course, shear strain. And of course, whenever we have a proportionality sign, we always remove that proportionality sign. And if we remove the proportionality sign, we always introduce a constant. The constant in this case is called the modulus of rigidity. Therefore, the shear stress tau is actually equal to G psi, where G is actually called the modulus of rigidity. Okay, let's call this equation 1. Let's call this equation 1. So I was saying earlier that if you observe this system now, we have here A, B, and B prime forming a triangle, making an angle here. So it means there is something we can relate about this point. Also, O, B, and B prime also forms a triangle. So let's pull out these triangles now and see what we can make, what sense we can make from them. Okay. All right. So let's consider triangle ABB prime. Consider triangle, okay, BA B prime. Let's consider this triangle BA B prime. So if we have that, we'll simply have something like this. This is A, this is B, and this is B prime. Okay, and this is the angle of shear, which is simply psi. Okay, we'll have something like this. Not forgetting that from A to B is actually the entire length of the cylinder. Not forgetting that, okay? From AB is actually the entire length of the cylinder, which is given as simply L, okay? So we'll have here to simply be L. All right. So of course, we know this portion, AB, which is the length. This is BB prime, is actually what directly opposite to this angle psi. So let's take the tangent of what that angle. Tan psi, tan of the angle of shear is now equal to, from trigonometry, is simply opposite. Opposite now is BB prime, so simply keep that BB prime all over adjacent AB, okay, all over AB. So we simply have this. All right, so therefore, BB prime, let's make BB prime subject. That's simply equal to cross multiplying. Let AB multiplies tan phi. Okay, so we have AB tan psi. Okay, we simply have this. Okay, so not forgetting, AB actually happens to be the length of the shaft. Alright, so we simply have that BB prime is actually what? L tan psi. Okay, now let's consider that the value of psi becomes so small. Okay, that's the shear deformation now, which is the shearing strain, becomes so small. So when psi is so small, okay, when it becomes so small, then the value of tan psi is equal to what? Psi itself. When that angle becomes very small, then the tan of that angle becomes that angle itself. That simply means now that I can rewrite this now as B prime is now equal to, this becomes L psi, because tan psi now is equal to psi, so it becomes L psi. Let's call this equation 2. Okay. Also, let's consider the second triangle. Okay, so let's also consider the second triangle from O, B, B prime. Let's consider this other triangle as well. Notice now, remember that from the center to any point on the cycle is actually what? The radius arm. So from the center of any cycle to any point at all on the cycle gives us the radius. So let's simply call here R. That's the radius from center to any point on the cycle. Same thing applies that from here to this point is also what? Radius arm. So let's consider now this triangle and see. Okay. So if we consider that triangle, um, we simply have this. Okay, this is the center O, this is point B, and this is simply what? B prime. This is the angle of twist theta. It was stated there earlier. Remember, from the center to any point on the cycle is simply what? The radius R. So simply call that R. As well, let's also find what the tangent of what this angle. We see that there's also a relationship between what BB prime, just like we had in the first case. So that means let's find the tangent of this angle. And if we do that, we are going to have that tan theta, which is the angle of twist, is now equal to opposite is BB prime as well. So you have BB prime all over adjacent is now what? OB all over OB. So just like here, if we make BB prime subject simply what by cross multiplying, we are going to have that BB prime is now equal to OB multiplies tan theta. We simply have OB tan theta. So we have this. But remember, OB stands for what? The radius arm. So this simply means that BB prime is actually what? R tan theta. Okay, so like we did in the first case, now when theta is very small, when theta is so small, then the value of tan theta still gives you the value of what? Theta. If theta becomes very small, then the value of tan theta gives you the value of what? Theta. That simply implies that we can now have that equation to be BB prime is simply equal to R theta. Let's call this equation 3. So you notice now that equation 2 and equation 3 are actually what? Same thing, because they are the same equation for what? BB prime and BB prime. So the two equations can actually be what? Equated together. Let's do that now and see. Alright, so since 2 and 3 are equal, since equation 2 and 3 are equal, alright, therefore you simply have r theta equals L theta, L psi, okay? R theta equals L psi. So we can now find the value of what? This shear strain. If we find the shear strain, we now observe that shear strain is actually what? Dividing through by the length. We simply have R theta all over length. So call this equation 4. Now recall from equation 1, okay? Recall from equation 1, we obtain that shear stress is equal to G shear strain, okay, where G is modulus of rigidity. Therefore, in place of this shear strain, we can now simply substitute the value as this. So that simply implies now that shear stress itself is now equal to, this becomes G, in place of shear strain, we have the value to be R theta all over length. It becomes G R theta all over length. Call this equation 5. Let's call that equation 5. We can also craft that from this equation. If we decide to divide both sides by the radius r, we are now going to have that shear stress all over radius is actually equal to g theta all over length. Let's also keep this equation aside. Call this equation 6. Okay, so we'll keep these two equations aside. Alright, so since we've obtained those equations, now let's now find the value for this torque. We said a torque is being applied to this surface which causes this shear strain or the shearing of this portion. Now, what is this torque? We know by definition that torque, okay, which is capital T, is actually what? Force times radius. This is what torque is all about. Torque is simply the force multiplied by the radius arm for every what? Shaft or cylinder. Okay, so if that is the case, then what is the force? Now, we said this torque applied here causes what? A shearing of this portion. So that means we have a shear stress here, which of course we obtained in first equation that the shear stress is equal to what? The shear strain. So recall now that shear stress, okay, recall that shear stress, um, which is simply tau, is simply what? Force all over area. Recall that shear stress is simply force over area. So which means the force causing this rotation, of course, lies in the shearing of the body. So this is actually what? That force, making F subject of the formula here by simply what? Cross multiplying area multiplies the shear stress. F is simply what? The shear stress times the area. But we are saying that this is a cylindrical portion. Of course, every shaft has a cylinder. it has a length and it has a radius, so it's actually a cylindrical portion. What then is this area of what this portion? Now we are considering a system, we are considering a small element of what the arrow. So that's why I labeled that up here. We are now considering a small element of thickness, the arrow. The thickness is actually what? The arrow. Okay, not forgetting the thickness is the arrow. So this actually means thickness. Okay, this is actually what the thickness. So we are considering an elemental portion, as can be seen here, of thickness, the arrow. Now, what is the area? So, of course, considering the spherical surface now, considering the spherical surface, the area for this sphere now is simply what? 2 pi r the r. Of course, this is the area of a sphere. So the area of this spherical portion simply gives us this 2 pi r the r, where the r is simply what? The given thickness of the material or thickness of the surface we are considering. So we are considering an elemental portion, a very small portion of thickness, the r. So this becomes the area. So if this is the area now, it means now that, okay, if this is the area, it means now that we can actually find the force. The force now becomes F is now equal to, we simply say it is shear stress times area. It becomes shear stress, okay, times 2 pi r the r. Of course, 2 pi r the r is the area of what? The sphere, okay. So force is simply shear stress times 2 pi r the r. So if we know this, we can now find the value of torque. Remember, torque is simply force times radius. So we've obtained this force now. Therefore, the torque becomes, okay, the torque becomes, okay, the torque becomes T is actually what? We said torque is force times radius, and we know the force. Force is simply this shear stress times 2 pi r the arrow now times what? Radius. Force times radius. So simply have that multiply. This is the whole of this value simply gives us the force times this radius. Okay. Okay, so from here now, of course, we'll have arrow here, we'll have arrow here. Let's bring them together. The torque becomes shear stress times 2 pi r times r d r. So simply dispositioning this, bringing this closer, because I have radius here, I have radius here. Let's multiply them together. All right, so I'll simply have that torque is equal to shear stress times 2 pi r times r here simply gives me r squared the r. So keep this equation aside. Now let's observe the previous equation we had. Let's observe what we obtained for shear stress. Okay, let's go there. Now recall from equation 5. Recall from equation 5, we obtain this value for shear stress, g r theta all over L. So recall from 5, we obtain shear stress to simply be g r theta all over L. Okay, so which means in place of this shear stress, I can replace with this what formula. So this simply implies now that the torque T is now equal to, in place of shear stress, we simply have g r theta all over length, okay, times 2 pi radius squared the r. We simply have this. Of course, we have arrow here, we have arrow square here. Let's also relate them together. I'll simply have that torque is simply equal to g theta all over length times 2 pi, okay, r squared times this other arrow here, arrow the r. And therefore, I can now find that torque is simply what? G theta all over length times 2 pi. This arrow square times arrow simply gives us arrow cube the r. So I have this. Alright, so to obtain the total torque on the shaft material, we simply what? Integrate. Now let's take a look at let me take us back to the diagram so we can observe something. Okay, so if we observe the diagram here, we said maximum stress occurred at this point, maximum shear stress. It can also be seen here, maximum shearing of what? The surface. So maximum shearing actually occurred at where? Diameter all over 2. So when we split the diameter from 0, okay, from 0 to d all over 2, all right, so we simply have what? Maximum shear stress. Of course, this is center. Center is simply 0. So from 0 to where? D all over 2. That's just shear stress is maximum. That means the maximum torque will also what? Take place at where? D all over 2. The maximum torque will also take place at D all over 2. So which means for us to obtain the maximum torque, we have to integrate that equation to where from 0 to D all over 2. That gives us the maximum torque applied on the system. Let's do that and see now. Alright, so to obtain the maximum torque, we simply integrate the whole of this equation from 0 to d all over 2. So integrate from 0 to d all over 2. Alright, so within this limit, we obtain the maximum torque on the system. Alright, let's do that and see. Alright, so maximum torque T is now integral from 0 to d all over 2 of the whole of this function g theta over L times 2 pi r cube the r. Okay, so once again, g is a constant called modulus of rigidity. Theta itself is the angle of twist, it's also a constant. L is a length, it's also a constant. 2 and pi are also constants. So let's bring all the constant outside of the integral sign, since we are integrating with respect to the arrow. So it means we have to integrate what? R cube with respect to the arrow. So send all the constant out. We simply have that torque is equal to g theta all over L times 2 pi, okay, into times 2 pi integral from 0 to d all over 2 r cube the r. So we simply have this. T is now equal to have g theta all over L times 2 pi. Now, of course, if we integrate r cube, we'll simply have r to the power of 4 all over 4. So put in your limit from 0 to d all over 2. Alright, so let's bring out this 4 here so that r4 is left alone. So we'll simply bring out 1 over 4 outside the bracket. We'll simply have T is equal to g theta all over L times 2 pi all over 4. Simply send out this 4 out. So we are now left in the bracket with r to the power of 4 from 0 to d all over 2. Alright, so notice that I'm not touching this equation. I'm not erasing this out simply because I will need it. So I'll fall back. I'll continue my integration over here. Okay, so I have here now T is now equal to g theta all over L. So from here, 2 can actually what go into 4. I'm left with what? Pi all over 2. Okay, of course, 2 goes here as 1, 2 goes into 4 is 2. Okay, now into r to the power of 4 from 0 to d all over 2. So let's put in the limit of integration now. Torque T is now equal to g theta all over L times pi all over 2. So put in the limit. Upper limit come first, and the upper limit is d over 2. In place of r here, we'll have d all over 2, but r here is to the power of 4. So all to the power of 4 minus lower limit. Lower limit is 0 to become 0 to the power of 4. So you have this, okay? So torque T is now equal to g theta all over L times pi all over 2 into d to the power of 4. Of course, this simply means d to the power of 4 and 2 to the power of 4. D to the power of 4 itself gives us d4 all over 2 to the power of 4 gives us 16 minus 0. Of course, 0 to the power of 4 remains 0. So you have this. So this actually T equals g theta all over L. Okay, this becomes pi d4 all over 2 times 16 here simply gives us 32. Okay, that gives us 32. All right, so we have this pi d4 all over 32. Now, this quantity pi d4 over 32 is known as the second polar moment of inertia. Okay, it's a term that is known as second polar moment of inertia. So where we simply use J to symbolize it. So where J equals pi d4 all over 32, okay, is the second polar moment of inertia. That's simply second polar moment of inertia. Okay, so it's simply called second polar moment of inertia. So we can replace pi d4 over 32 by what? J. And if we do that, let's continue over here. Okay, so if we do that, now in place of this equation, we simply have T equals g theta all over L times J, where J stands for pi d4 over 32. Alright, so let's now divide both sides by what? J. If we divide through by J, we simply have T all over J is equal to g theta all over L. Let's call this now equation 7. Now observe that equation 7 and equation 6 are the same. So observe that equation 7 and equation 6 are the same. We have g theta over L to be equal to T over J, and same thing here, we have g theta over L to be equal to shear stress over radius. So this simply now implies that from here, T all over J equals g theta all over L. Meanwhile, g theta over L, as can be seen here, is also equal to shear stress all over radius. Is equal to shear stress all over radius. Alright guys, so this equation is what we call the torsion equation. Alright, so that equation is simply called the torsion equation. So that's how you derive the torsion equation. I hope you find this video very interesting. Please, if you do, don't forget to share your thoughts in the comment section. Of course, if you're new to the channel, please do well to hit the subscribe button to keep getting updates on content as is. I will see you in the next video with solutions and problems on how to apply what the torsion equation. Alright, thanks guys.